The modern storage battery is a concentrated source of electricity that symbolizes man's efforts to better his life through the control of nature's power resources. Here is a means of storing energy and using it when we want it. The automobile storage battery supplies the electrical energy to start the car engine and gives standby power to operate the lights, the radio, and the other electrical accessories of the automobile. Huge storage batteries are part of the power plant of the atomic submarine. Small storage batteries help control giant guided missiles. Storage batteries power ocean buoys to help guide mariners in dangerous waters. In hospitals and in public buildings, storage batteries supply standby emergency power. There are many different kinds of batteries doing many different kinds of jobs. Yet, the principle upon which these storage batteries work is the same. What is this principle?
The storage battery is an electrochemical device for storing energy in chemical form so that it can be released as electricity. Now, the principle of operation is simply this. Two unlike metals, when immersed in an acid solution, create a chemical reaction. One product of this reaction is released electrons that make up an electrical current. The two unlike metals could be copper and silver, for example. Now, as for the acid solution, here's one source. The citric acid in an ordinary grapefruit. Immersing this quarter and this penny in the grapefruit has created a battery. Yes, it has. Here actually is a source of electricity. And its current, though very small, can be measured. So you see, this is a battery. It hardly produces enough electrical current for any useful purpose. Nevertheless, these two batteries operate on the same basic principle. The two unlike metals may be copper and zinc. Now, these are immersed in dilute sulphuric acid, a much better electrolyte than the citric acid of a grapefruit. Again, the resulting chemical reaction produces electricity. Now, this is a stronger battery, approximately 1 volt. Yes, two unlike metals immersed in an acid solution will produce a measurable electrical current. The discovery of this principle goes back more than 150 years to the famous Italian nobleman Alessandro Volta, often called the father of modern electrical science. In 1800, he invented the voltaic pile, the first electric battery. This consisted of a series of discs, zinc, silver, and cloth soaked in the electrolyte, which was brine. The more discs, the higher the voltage. And some of these early voltaic piles were more than 6 feet long. This primitive battery opened up a vast area of experimentation and research, but it had very marked limitations. First of all, its power output was low, and the metals used, silver and zinc, wore out too quickly. As in our experimental cell, after a short time, the zinc plate, as you can see, is almost consumed by the electrolyte. Now, you can't charge a battery like this because it's a primary battery. It can be discharged only once, and then its usefulness is ended. This is the principle of the flashlight cell. But the storage battery needs plates that will stand up for a long time and can be discharged and charged again and again. The answer is the lead plate, first developed by the French scientist Gaston Planté in 1859. These lead plates, when immersed in our electrolyte solution, make up what is called a secondary, or more popularly, a storage battery. It can be charged and discharged over and over again. Why? Because lead is not consumed when immersed in an electrolyte of sulfuric acid and water. But there is no chemical reaction going on here. Remember, these plates are lead, both of the same metal. And it takes two unlike metals in the electrolyte to make electricity. So, what do? We change these plates to make them act like unlike metals by charging them. The battery is now being charged. Are we storing electricity in the battery? No. Actually, we're making chemical changes in the plates so that they can produce electricity. The current from the battery charger is converting plates of like metal into plates of unlike metallic compounds. Several hours are required for the charging. When the charge is completed, these plates are no longer alike. Now, what has happened? This plate has become the positive plate. Its color has changed from gray to dark brown because a chemical reaction has taken place in which the lead on the surface of the plate has changed to lead dioxide, usually called lead peroxide in the battery industry. This plate has become the negative plate. It is still lead, as it was before charging. So now, we have two unlike forms of the same metal, lead and lead peroxide. In a storage battery, these will work in the same way as two completely unlike metals. Now, the voltage of this battery measures approximately 2 volts. A battery with plates of this kind can be charged and discharged over and over again. Remember, a storage battery does not store electricity. It just appears to do so. Actually, a storage battery stores energy in chemical form, which it releases as electricity, and it can do it repeatedly. Let's look at a schematic diagram of the chemical reaction that releases this electrical current. In this beaker, we have the electrolyte, dilute sulfuric acid. Here is the positive plate of the battery, lead peroxide. Here is the negative plate of the battery, plain metallic lead. Now, let's consume the electrical energy this battery creates by placing a light bulb in the circuit. When the switch is closed, the circuit is completed. The current flows and the light bulb lights up. Remember, the battery supplies this electrical current through a chemical reaction. And during this process, it is being discharged. As long as we're watching a chemical reaction, let's refer to these materials by their chemical names. Pb means lead, but PbO2 means 1 atom of lead and 2 atoms of oxygen, and that makes lead peroxide. H2SO4 means 2 atoms of hydrogen, 1 atom of sulfur, and 4 atoms of oxygen, and that makes sulfuric acid. H2O means 2 atoms of hydrogen and 1 of oxygen, and that makes water. And PbSO4 means 1 atom of lead, 1 atom of sulfur, and 4 atoms of oxygen, and that makes lead sulfate. When the battery is discharging, an electrochemical reaction is taking place. As soon as the switch is closed, the two atoms of oxygen in the PbO2 break away to seek some other chemical with which to combine. At the same time, the SO4 of the electrolyte combines with the chemicals in the plates to form PbSO4, lead sulfate. In the meantime, the two atoms of oxygen, the O2, separate, each combining with an H2, two atoms of hydrogen, to form H2O, which we all recognize as the symbol for water. As this chemical reaction takes place, electrons are released. These make up the energy that gives us our electrical current. That's all there is to it. The battery is discharged and the lamp goes out. We now have two like metallic compounds. Both plates are PbSO4, lead sulfate. What's more, they're immersed not in an acid solution, but in H2O, plain water. And like metals, in plain water, do not produce an electrochemical reaction. This is what happens when we discharge a battery. Now, what happens when we charge it? Let's put a battery charger into the circuit instead of this light bulb. Electrons are returned to our cell, and the reverse of the discharging electrochemical reaction takes place. The oxygen atoms of the water break away and form O2. The SO4s break free from the plates and reunite with the H2s to form the electrolyte, sulfuric acid. While all this is going on, the O2s return to the positive plate to form PbO2 again, lead peroxide. The negative plate becomes Pb, lead. Now, notice the plates again act as unlike metals immersed in an acid solution. Our battery has been recharged. This is what happens in the storage battery. Behind this development is the work of men like Charles Brush and T.A. Willard. Although the electrochemical principles are the same for both of these batteries, there are many, many differences. Let's look at these differences for a moment. Here is a small and compact version of a modern storage battery, much smaller than an automotive battery, but it is almost identical in construction and operation. Now, what is the difference between this battery and this battery? This experimental cell is hardly more than a laboratory curiosity. If you tip it, it spills. Turn it upside down, and it literally falls apart. But this modern battery is a compact, sealed package. It's practical and durable. It will operate in any position, on its side, on end, even upside down. And it's leak-proof. These are obvious physical characteristics. Now watch the difference in electrical characteristics. Here we have two ordinary 6-volt fog lights. One I'll light up with our experimental cells hooked up in series. This one I'll connect to this modern 3-cell 6-volt battery. Even while I'm talking about it, the light connected to the experimental battery is beginning to dim out. In less than half a minute, it will be out. The light connected to the modern battery burns brightly and will continue to do so for a half hour or more. Why does this modern battery give so much more electrical current? What makes the difference? The main difference is in the plates. There are only 2 plates in each cell of this experimental battery, against 9 plates in each cell of this modern battery. 4 positive and 5 negative plates. Each plate contains many times more active material than does the experimental plate. This plate from the experimental battery has only a thin coating of lead peroxide, the active material in the positive plates. If you scrape off all the active material, it doesn't make a very big pile. The modern plate starts with a lead casting, or grid as it is called. The ingredients that make up the active material are mixed together to form a stiff paste, which is applied to the grid, filling every open space. When the active material dries and hardens, it becomes extremely porous, permitting deep penetration by the electrolyte, and consequently producing more electrochemical reaction. This is true of both positive and negative plates. After drying and hardening, the plate is charged. The charged plate is more than 50% active material. With so much more active material, it's no wonder that the modern plate delivers so much more electrical current. Of course, the larger the battery, the larger the grid. This is a grid for an automotive battery. You'll notice that the horizontal grid bars are triangular in cross-section to seal all of the active material firmly into place. Precision design and construction details like this, and many of them are incorporated in today's battery, are not readily apparent to casual observation, but they are important. Remember, this modern battery employs the same principle as the first battery ever built. Two unlike metals in an electrolyte create a chemical reaction that produces electricity.
Much experimentation and research has brought the battery from this simple beginning to the modern storage battery we use today. Yet research still goes on. Scientists, engineers, and technicians are working to make batteries smaller and even more powerful. They are developing batteries to work under the most adverse conditions. They are developing new principles of design and operation through the tools of modern science. Such research is also directed towards the discovery of new materials and better manufacturing methods. Modern mass production of batteries starts with the grid. Lead, alloyed with other metals, goes into automatic molding machines to make the grids. The grids are cast in pairs for easier handling. Meanwhile, the active material is being prepared. Chemically pure lead is converted to lead oxide and ground to a precise texture that assures maximum penetration by the electrolyte. This lead oxide is mixed into a paste that is carefully compounded to retain the highly porous characteristics and permitted to be applied evenly and compactly into each grid cavity in a fully automatic pasting operation. As the pasted grids, now called plates, move away from the pasting machine, they undergo controlled heat treatment that removes excess moisture. Some of these plates will be charged and used for making what is known as the dry charge battery. The remainder will be used as they are for making wet charged batteries. Other parts of the battery are made with equal precision and care. Automatic rotary casting machines turn out cell connectors, plate connectors, and other metal parts to fit batteries of all sizes and shapes. Not only are the battery components inspected by the workers on the production line, but samples of finished components are laboratory checked on a continuing schedule. The first step in assembling the battery is making the element. The negative plates, separators, and positive plates are alternated and positioned in exact numbers. The separators prevent the negative and positive plates from touching, a condition which would short-circuit a battery. Welding, or burning as it is called by battery men, connects the plates into groups, which, along with the separators, make up what is called an element. One element is used in each cell of a battery. The 6 elements of the 12-volt automobile battery are inserted in the rubber case and then tested to make certain that assembly and welding are correct. The batteries move on for cell covers, cell connectors, battery post molding, and connector burning. Then comes double sealing with a special compound that withstands the heat of summer and the cold of winter. For wet charged batteries, the electrolyte is added at the factory the battery is charged, ready for installation in an automobile without further preparation. For dry charged batteries, the electrolyte is added by the dealer when the battery is placed in service. Wet or dry charge, the modern storage battery is manufactured to exacting specifications to assure long life and dependable performance. Batteries taken right from stock are spot tested under conditions far more grueling than ever encountered by a motorist. They're tested on special apparatus that measures battery life and consistency of operation under extremes of temperature colder than the Antarctic, far hotter than the tropics. The modern battery starts out with every advantage that built-in quality can give it. But in an automobile, the battery is not a completely independent unit.
Honey, I can't get the car started.
What's the matter with it?
Well, I don't know. It just won't start. Well, maybe it's the battery.
The battery? We just bought it on the last trip we took. What's happened to it?
I don't know. It just won't start.
Don't worry. Call Eddie's service station and have them take care of it.
I don't see why I should need a new battery.
Well, your old battery, I'm afraid, is ruined. Won't even hold a charge.
I don't know why. I thought a battery is supposed to last longer than a year.
Ordinarily, Gil, it should.
So why didn't mine stand up?
Well, there are a lot of possible reasons. Now, it may be here in your car's electrical system. And your battery, of course, operates in conjunction with the other electrical units in your car. It could have been caused by worn insulation in the wiring, or by an improperly adjusted voltage and current regulator, or by the stoplight switch, by a faulty starter. It can be caused by a faulty generator, by corroded battery cables, or by a short circuit anywhere in the electrical system. The lights, the accessories, any of these things. Any little electrical leak can run a battery down if the car's out of use for 4 or 5 days. And, of course, it's possible to abuse a battery without realizing it. Here, look at this. Loose hold-downs in the battery carrier cause damage to this battery. When a battery bounces and shakes in the carrier, the case may be damaged, and the battery posts can be broken. Or a battery can be dry, such as yours was. Now, I've added water and tried to charge it, but it just won't charge. See? Now, this is your bad cell. Now, after a battery has been dry too long, this is what's likely to happen to the plates. Above this line, the plate has been dry, overheated, and probably ruined. Now, here's what a good plate looks like. Here's a plate from a battery that was allowed to remain in a discharged condition. These hard, insoluble sulfate crystals on the plates usually mean that the battery is ruined. It can happen to new batteries as well as to old ones. Now, here's a plate from a battery that was overcharged in the owner's car. Overcharging causes the plates to disintegrate. This one is completely ruined. A battery in good condition is important to you. It means quick starting, which conserves gas. and also conserves the life of your car engine. What's more, quick starting conserves the life of your battery, too.
Okay, I guess I better have a new battery. Do I get a trade-in allowance on the old one?
You most certainly do. Your old battery's worth money.
What do you do with the old battery? Junk it?
There's a lot of lead in that old battery. It'll be refined and used over again.
I understand.
They tell me that about 1/4 of all the lead used in this country every year comes from the lead that's salvaged from these old batteries.
Here's the battery for your car, Gil.
That's the story of the modern storage battery, a concentrated package of power that works for us in dozens of ways every day. In transportation and communications, in science and in industry. Yes, the storage battery is at work for us in many ways. The story of the storage battery began more than 150 years ago with the voltaic pile. This story will go on and on as the storage battery does more and more for us, helping us in our never-ending search for improved sources of energy to make our standard of living a better one.